These are the lecture notes for cryptography for the SADIT project. This is the first module, which is an introduction to the topic of cryptography. In this module, we will introduce what cryptography is, and we will also look briefly at the history of cryptography. So to open with, let's consider some of the recent news items related to cryptography. In April of 2018, there were several news articles related to crypto, and there are three of them that I would like to just discuss briefly. The very first one, which made a lot of news in many different mainstream and blog sites, was Ray Ozzie suggesting a secure backdoor to smartphones, and his interview appeared in Wired magazine. Ray Ozzie, for those of you who may not be familiar with his name, was the chief technical officer at Microsoft and also the chief software architect for a while. He is very well regarded in the technical community, and he was responding to this recent issue that has been discussed in many different places, where law enforcement authorities are unable to access the content on smartphones because Apple, Google, and everybody else is putting strong encryption or crypto on these phones. So unless the law enforcement authorities have the passcode or the fingerprint to unlock the phone, they are unable to see what is inside, even if they get the hard drive out. So what Ray Ozzie was suggesting is that there would be some kind of a backdoor which would be opened by a secure master key, and this master key should be kept securely in the organizations that sell the phones. So for example, Apple would have a master key to open all iPhones, and maybe somebody like Google would have a master key to open Pixel phones, and so on. There's a lot of pushback here because there are no guarantees that such master keys will remain secure forever. In case they get leaked, and not necessarily into the hands of the good guys, but maybe perhaps into the hands of the bad guys, then it's quite possible that all of our phones will be now subject to attack by these bad guys. And so there is this discussion that is going on as to how to solve this problem of law enforcement versus privacy of individuals. The second news item is also related to something in the same direction. Google is trying to introduce an app called Chat, which can replace the short messaging service app on Android phones. The reason they want to do this is because this new app called Chat, if it is supported by the service providers like AT&T and Verizon, can show the information that you typically see with other kinds of more advanced messaging applications like iMessages for Apple. But the problem with this chat app is that it does not have end-to-end encryption because it's relying on the short messaging service protocols that Verizon and AT&T are and other service providers are using. And so there has been a lot of talk about whether or not this is a good idea and whether Google should have done something to enforce end-to-end encryption. Again, end-to-end encryption here implying that the conversations between two individuals will remain private. The last news item that I would like to talk about here is what people are referring to in the mainstream media as crypto crime waves. And this has nothing to do with the technology of cryptography, but with the implications of some assets that crypto has enabled, in particular Bitcoin. Bitcoin, the price of Bitcoin has gone up significantly in the last 1.5 years. People who bought Bitcoin at low prices, maybe 5-10 years back, have now become extremely rich. But once they become extremely rich, you know what happens. There are people who are trying to steal the money from them, steal the bitcoins from them. And so the crypto crime waves that people are referring to here are attempts to get the passwords to their Bitcoin wallets so that they can steal these bitcoins from these individuals. And this they are doing using traditional crime, like stealing, mugging people, entering their homes, and so on. outside of these three news items that we just briefly talked about, crypto is also seen in daily life in many different places. For example, whenever you browse the internet today, many of the more common sites like Google, CNN, or MSN.com, they try to take you to these sites with using secure protocol. So if you see the lock in your browser, it is using a secure protocol called transport layer security, or TLS, and that tells you that the communication between your browser and that website is secure. If you have ever used BitLocker on a Windows computer or FileVault on a Mac, then you know something about file encryption. So what BitLocker and FileVault do is that they encrypt the information that is stored on your hard drive. So suppose somebody steals your computer and they extract the hard drive and try to read it because they don't have your password to access the files through the operating system. They won't be able to read anything useful because all of the information is encrypted using either of these technologies. Also, most of us have several accounts on the internet, maybe tens, maybe even 100. And for all of these accounts, we somehow need to remember passwords. And that's a huge problem for us. So many of us use password managers. A password manager that is fairly popular, and it's available on Google Play as well as the Apple iTunes Store, is 1Password. If you go to 1Password's website, it says that it is storing all your passwords using 256-bit AES encryption. So what is 256-bit AES encryption and why is it 256 bits? These are some of the topics that we will try to cover later in the other modules. Next, I would like to talk about cryptography in context of some of the terminology in security that you might have already seen in other modules. So if you remember, there was a huge breach of credit card information in Target, especially during the holiday season in December 2013. And the mainstream media reported that debit cards were not as impacted as credit cards because, first of all, you have to use a PIN number with a debit card. And these PIN numbers were encrypted and stored, which means that even if people had recovered something related to the debit cards, like the debit card number, the PIN numbers themselves were not available because they were confidential. So this is an example of a security feature called confidentiality, where unauthorized people are unable to access the information simply because it's been encrypted and they don't know the key. If you have cashed a check at a bank, they probably ask you for your driver's license. They want to make sure that you are who you claim you are. And this process is called entity authentication or identification. If you pay bills using online banking, where you use a password, or if you receive a text from your bank with a code to verify the fact that you're indeed the person that you claim to be to log in, these are also other examples of entity authentication. Crypto plays an important role in this security feature called entity authentication. How do you know if you're really connecting to a website such as Amazon.com? Maybe somebody is listening to you in the middle, and maybe they're changing the data as you're sending it from your browser to Amazon.com. How can Amazon.com make sure that you're indeed asking for what you are saying that you're asking for? And how do you know that Amazon.com is responding in the correct way? So this is an example of integrity. Here you're interested in making sure that the content has not been fabricated or changed, and crypto plays an important role here as well. In fact, cryptography is part of the enabling solution for many of these security features or services like confidentiality, authentication, and integrity. It's also used in many other places. For example, storing and verifying passwords. You really don't want to keep the passwords in plain text form, because in case it gets leaked, then now all of the passwords are known to the bad guys. So typically they use one-way hash functions to store these passwords. These are not really encryption, but they use similar principles, and we will look at what they do in a later module. If you look at digital documents, which need signatures like physical documents, you simply cannot attach your signature to these documents because these signatures can be forged, especially they're just bits zeros and ones, you can just copy the zeros and ones. Somebody else can copy it. So you need to have some kind of a binding between the content in the document and the signature. And that is also enabled using cryptography. Many of you may have heard of Bitcoin, and you may also have heard of blockchains. The blockchain technology is what enables Bitcoins. It's essentially a distributed ledger, which means that people are writing, many different people are writing into the same ledger in the transactions that they're doing with each other. And these transactions that are being recorded in the ledger, they're secure from tampering, which means that somebody cannot go in and change things to make more money or to uh, cheat somebody else. Now, all of the things that we have talked about so far, they make use of keys. When we talk about keys, these are strings of binary numbers, binary bits. And in order to make sure that people have the right kinds of keys, you need cryptography. So it looks like a chicken and egg problem, but as long as there are certain techniques that are well understood and there is a certain level of trust in certain entities, it is possible to make use of cryptography for key establishment as well. Now, a brief history. Before we start the history, I would like to make a statement regarding the difference between camouflaging, concealing, and ciphering. For thousands of years, people have used methods of concealing information, and I just want to again emphasize here that concealing is not the same as encryption or ciphering. For example, in old times when it took maybe months to go from one village to another, they would shave off somebody's head, they would tattoo the message on his head, and they would allow the hair to grow as he traveled so that if people caught him, they would not find the message. Time was not at a premium then. Today there is this science or art called steganography, where you're hiding information in the midst of irrelevant data. So you may have a small piece of text inside a beautiful picture of the Old Faithful. This is not cryptography because this requires a lot of overhead. You're essentially trying to hide a needle in a haystack. And so in many cases it's useful because it hides the very existence of secret communication, because people don't know what to look for and where to look for unless they have previous knowledge of what exactly is going to be done. So going back to the history of encryption itself, in biblical times, around 500 BC or so, people knew how to substitute one alphabet by another in a systematic way, or letters in an alphabet by other letters in a systematic way. In Sparta, where we had the Greek city-states, they used a device called a citali. A citali is like a block of wood or a cylinder of wood, and you would tape a ribbon around it or something like that, and you would write on the ribbon. When you unravel the ribbon, the letters would all be scrambled, and so it would be difficult for somebody to make out what the message was unless you wound it up again on the same cylindrical block. And so this was a technique that the Spartans used to securely communicate. The Caesar cipher, which is an example of a shift cipher that we will look at later, was described by Julius Caesar in 50 BC. A mechanical cipher disk was invented by Leon Battista Alberti in 1470. And in 1585, there was a person called Wiesner who created an auto-keyed cipher, which means that it would use the message itself as a key in order to encrypt the information. So there is a belief that the most secure type of encryption, called the one-time pad, was invented in 1917 by Vernam. But recently, in about 10-15 years back, people found other evidence which indicated that this approach was known previously by a person called Frank Miller in 1882. So there is a sharing of credit here for who created the one-time tape, the one-time pad, which is considered to be the unbreakable encryption scheme. But a lot of advances in encryption really happened during the two world wars. There were many new ciphers that were created. The German military created a product cipher called the ADF GVX code in World War I, which was broken by the British uh, cryptographers. And these linkages between World War and cryptography and mathematics extended beyond that time. Information theory, which was invented by Shannon, played an important role in defining the notion of perfect secrecy, which is in fact tied to the one-time pad. And in modern times, we have seen great advances in encryption schemes. Till around 1976, all of the encryption algorithms, including the ADF-GVX code and other encryption schemes that we have talked about, like the shift cipher, they were all secret key algorithms. Some people also call them as private key algorithms or symmetric key algorithms, because the two communicating parties, they should have the same key. In 1976, Whitfield Diffie and Martin Hellman introduced the very first public key algorithm, which is called Diffie-Hellman key exchange in 1976. And RSA, which is the most popular public encryption scheme in use today, was invented in 1977. But the mathematics behind these schemes was originally discovered in the 1950s. They were kept classified by the intelligence agencies in Britain and probably in the United States, even though we don't know much about what was happening here. In 1977 also, the very first standard for cryptography got published by the National Institute of Standards and Technology, and this opened a new area of research, because till then people had not really seen a modern encryption scheme in an unclassified form. It was a symmetric key algorithm. It survived for almost 30 years, 25 years at least, and it's used in some forms even today in some places. We will talk about that when we come there. In 1987, people discovered elliptic curve cryptography, which is a public key algorithm which uses smaller key sizes compared to RSA. In 2001, the data encryption standard, which was very successful, was replaced by the advanced encryption standard. This is AES that we talked about when we talked about 1Password. We talked about hash functions for storing passwords. The secure hash algorithm, the version 3, if you want to call it that, was published in 2015, and it's the emerging standard for hash